Have you ever been using an electronic tuner and noticed this weird number pop up?
Like a two-headed horse.
Have you ever been picking or bum-didding along when you notice strings slightly out of tune, only to realize that all your strings might be slightly out of tune?
Does a one-legged duck swim in a circle?
Have you ever wondered if maybe your banjo is just broken somehow and everyone else's banjos aren't?
Do bears wear funny hats?
Never fear, my intrepid pickers, we'll get to the bottom of all these dilemmas and more in this lesson. Howdy folks, Banjo Dan here with another installment of the Eclectic Banjo.
And I'm Franklin Danny. So far in the Eclectic Banjo's Guide to Music Theory series, we've been taking relatively small bites out of the whys behind the whats on the banjo.
Lesson 6 will be taking our first pretty big bite into the relationship between music and mathematics, with the goal of greater understanding of your banjo's palette. This lesson should fill you up on the main points about frequencies in music, give you a sizable portion of not one, but two kinds of temperaments, and hopefully leave you satiated knowing that your banjo isn't defective in some way. I can just smell the pleasant aromas coming from phenomenal learning opportunities now. When things vibrate, it causes air molecules around it to move back and forth, creating sound waves. If there are no air molecules present, such as in outer space, then no sound waves are produced.
And the Star Wars franchise has been lying to us all this time.
Sound waves are quantified by their number of vibrations, or cycles per second, called its frequency, and measured in hertz.
Were those frogs and insect noises?
Oh no, those were higher planar sound wave resonances. Pitch is positively correlated with frequencies, and is the subjective perception of sound waves. Every note in music contains pitch. A lower frequency sound wave has a lower pitch, and a higher frequency sound wave has a higher pitch. If a sound wave's pitch is in the range that humans can hear,
then it can be heard!
For example, the 440 Hz on electronic tuners refers to the A above middle C in octave 4. Different musicians may alter the frequency of A4 depending on which tuning schema they're employing. We'll look into a couple of these temperaments later in this lesson. However, for most banjo players, keeping the tuner set to 440 will be the standard. Now, in order for a sound to be classified as musical, it needs to contain both a recognizable pitch and a sustainable duration. Let's explore some sounds on the banjo, and you tell me if they sound musical or not.
Oh, for sure. Yeah, totally. Okay. Passable. I'm on the fence with that one.
All these sounds have various frequencies that could be plotted on a graph. While the human ear can hear a wide range of frequencies, 12 mathematically balanced pitches with harmonious intervals have surfaced over time.
First the 7 notes A through G, and then 5 more sharps and flats, I believe.
Someone's been watching the Eclectic Banjo channel. Each grouping of 12 notes is called an octave. These 12 notes repeat themselves over and over again for as long as the human ear has the capacity to hear them.
What's that, Sony?
In standard G tuning on the banjo, there are 3 full octaves.
2 full octaves and a major 6 to be exact. I learned that in this thing right over here.
The banjo starts on its lowest note, the open 4th string D in octave 3, and rises to its highest note, the 1st string 22nd fret C in octave 6.
That reminds me, what do you call a pull-off made at the 3rd octave C?
Beats me.
C3PO!
One thing to keep in mind about the octave reference system. A new octave begins at every C note.
Wouldn't it make more sense to start at the beginning of the musical alphabet, at A?
In theory.
Was that a music theory joke?
In theory. Throughout history, people have been playing music. It's as fundamental as the sun shining, the rain falling,
or the banjo possessing a world-class timbre.
Try Trying to reproduce notes accurately on an instrument has been nearly an age-old constant as well. Temperament refers to the tuning system used to divide the aforementioned octave into 12 notes with reasonably harmonious relationships with each other. Several tuning systems have been proposed over the years to correct for one flaw or another in each predecessor system, or to specialize note reproduction on certain kinds of instruments. We'll look at two of these tuning systems now, Pythagorean and Equal Temperament.
Pythagorean.
Pythagoras of Samos, a first-class philosopher and mathematician, lived around 2,600 years ago in ancient Greece. He was one of the first intellectuals of his day to apply math to something other than currency or cooking. You might have heard about his theorem, a squared plus b squared equals c squared. Now keep in mind that the standard Western musical alphabet, or the diatonic scale, or frequencies haven't been postulated yet. He used a one-stringed instrument called a monochord to determine relationships and intervals between sounds.
Could we do a quick review on intervals?
Sure. The G major scale is a 7-note diatonic scale. Its notes and interval structure were postulated roughly 1,000 years after Pythagoras' time, give or take 500 years.
Basically, the internet has no idea.
Basically. Scale degrees can be used for each note, representing an ordinal relationship from the tonic G, or the first degree. So the A is a second from the tonic, the D is a fifth from the tonic, and so on. A half step is the smallest increment between an interval using the musical alphabet. 4 half steps equal a major third interval from G to B, 7 half steps equal a perfect fifth interval from G to D, 12 half steps equal an octave interval from G to G. Now where was I? Yes, Pythy.
Pythy?
Do you know how cumbersome it is to type Pythagoras over and over again in the script? Pythagoras, Pythagoras, ugh, I can just feel my fingers ache. Anyway, he deduced that a sound has the same harmonic equivalent at half its length on a string. So for a monochord with a scale length of, 26.5 inches, its octave G one pitch higher is at its halfway mark, or 13.25 inches, a 2-to-1 ratio. Now this 2-to-1 ratio between octaves is a mathematical constant. It doesn't matter what sound on a string you start with, its octave will always be at double and half its length on its scale. He also discovered another extremely consonant sound at what is now referred to as a perfect fifth interval above the octave. If the original scale length of 26.5 inches is divided by 3 and then doubled, which describes a 3-to-2 ratio, we arrive at the 17.66 inch mark for the perfect fifth D above the octave G. Similarly, we could do the same math using octave G at the 13.25 inch mark, and find another perfect fifth interval from G at the nut to D at 8.83 inches. Now, as it turns out, Pythagoras was able to come up with his own 12-note scale using the 2-to-1 octave ratio as a starting point and 3-to-2 ratios thereafter. It doesn't matter what the starting note is or even what octave reference point we use. For simplicity's sake, though, I'll use the middle C with a coefficient of 1.000000 for C4 and 2.0000 for C5. Now, before we get into the weeds with math, let me state from the outset that the Pythagorean scale has at least one very awkward drawback, called the Pythagorean comma. Comma in music parlance denotes a minute interval or difference of pitch, such as two inharmonically equivalent notes like C sharp and D flat. Recall our half-step discussion from earlier. I mentioned how half-steps are the smallest increment in an interval. That's true as long as you're moving between pitches using the musical alphabet. But a quarter step or quarter tone can be a measurement on a scale using smaller increments of pitch. And while a quarter tone is a lot harder to hear than a half or whole tone interval, it can create noticeable dissonance when playing chords of 2 or more notes. The comma represents just such an interval. At roughly a quarter step wide, or 25 cents, or 1.0136 coefficient multiplier, or 531,441 to 524,288 ratio, depending on one's preference.
I heard 25 cents and Couldn't we all use a little change?
This comma interval exists at every inharmonic location. This means that all otherwise inharmonic notes in temperaments that have them as equal in pitch to each other, such as equal temperament, are not actually the same exact pitch in Pythagorean temperament, resulting in more than a 12-note scale.
Kind of like a 17-note scale?
And the reason for this is because perfect fifth ratios are derived differently based on which note one jumps from. For instance, from B to F sharp results in one ratio, 729 to 512, or a 1.4238 coefficient, but from G flat to D flat results in a different ratio, 1024 to 729, or a 1.4047 coefficient, creating a discrepancy that can be explained using the comma's coefficient multiplier of 1.0136, and explaining why the two inharmonic values are not equal. Now back to our regularly scheduled programming. The goal for the Pythagorean scale is to divine 11 more notes by jumping to new perfect fifth intervals away from C, determining their cumulative ratios, and then using factors of 2 to bring their ratios in line with a coefficient value between 1 and 2.
What language did you just say that in?
Don't worry, I have some spreadsheets coming up to help with this process step by step. Because cumulative ratios get pretty large the further away you move from the starting position, we'll ascend the perfect fifth scale for the first 6 jumps by multiplying 3 over 2, and descend the scale of fifths for the final 5 jumps by multiplying 2 over 3. The right-hand chart shows all the jumps by their cumulative ratios and with factors of either doubling or halving the pitch to get them back in line with octave 4. For instance, the perfect fifth jump from C to G results in a 3:2 ratio away from 1, which equals 1.5. That stays within our desired coefficient zone between 1 and 2, so nothing more is needed. From G to D, we need to multiply 3 over 2 by another 3 over 2, representing 2 total perfect fifth jumps forward. This equals a 9:4 ratio, but is also outside our coefficient zone at 2.25. Thus, we need to divide the value by 2, or double the consequent value of 4 to 8, resulting in a 9:8 ratio. Each jump thereafter is another multiple of 3 over 2, with additional divisors of 2 based on which octave the perfect fifth jump lands in.
Will this be on the test?
For the blue arrow jumps, we need to multiply by 2 over 3 since going backwards results in a 2 to 3 ratio. So from an inverted fifth C to F, the ratio is 4 to 3. Dividing 2 by 3 yields a 0.66 repeating, taking it into octave 3. But now the antecedent needs double to get it back in line, or 2 times 2, resulting in a 4 to 3 ratio. Finally, all coefficient values outside of octave 4 need to be brought back to the center. And what we get is the Pythagorean 12-note scale using perfect fifth intervals. Pythagorean temperament produces extremely pure tones at perfect fifth intervals.
What about the other intervals like major and minor thirds?
Ah yes, remember there's a term for that. The dastardly Pythagorean comma.
Shh, not so loud, it might hear us.
This makes jumping from key to key on a stringed instrument without replacing your fret locations impossible since inharmonic notes are not equal to each other. Recall from our previous example in the interlude. Consider the perfect fifth jump from B6 to F sharp 7, resulting in a 729 to 512 ratio, which makes the coefficient 1.4238. G flat 0 is derived by descending in perfect fifths from D flat 1 and is a whopping 1024 to 729 ratio.
If you think that ratio is whopping, just wait for it.
And a coefficient of 1.4047. And the Pythagorean comma, with a ratio of 531,441 to 524,288, or 1.0136 coefficient multiplier, which explains the two numbers quite well, I must say. Another drawback to the Pythagorean temperament is that the intervals are derived from ratios that gradually increase in complexity the further away from the center one travels. Complex ratios are really hard to measure on a fretboard.
Banjo Dan, is there no hope at all?
Fortunately for you, Frail and Danny, there is another tuning system that most banjos use called Equal Temperament. And even more fortunately for you, this explanation will be a lot shorter. Equal temperament divides an octave into 12 equal semitones, or half steps. Because notes are equally spaced apart from each other, and inharmonic notes like F sharp and G flat have the same value in pitch, playing in different keys becomes a lot simpler.
Does math work like that? Equal semitones?
Well, as it turns out, you can get away with pretty much anything in math, as long as you don't need your numbers to be too exact. Equal temperament uses 12th roots of 2, which equally spaces out the 12 notes in an octave and gives each set of enharmonics the same coefficient to boot.
Hence the name equal.
It really is just a trade-off, or the lesser of two weevils, as Jack Aubrey would say. Is your banjo perpetually slightly out of tune? Yes. Can your banjo play in different keys without overhauling your fretboard? Yes. Will other instruments, also in equal temperament, sound relatively in tune when played together? Yes. So don't fret, my astute viewers, your banjo is not out of tune. It's your temperament that needs an adjustment. And there you have it, folks. I hope you enjoyed this lesson as much as I enjoyed constructing these charts and tables.
And if you appreciated my contributions to the video, clicking that like button would be like giving me a pat on the back. So, yeah, go ahead. Click it. Yes, it's right down there. Just click it. You know what I'm talking about. Just click it. That's it.
If you like this kind of content, here's another enthralling video about music theory and how it applies to the banjo.
On behalf of Banjo Dan and myself, we'll see you next time right here at the Eclectic Banjo.